So we've spent a lot of time talking about the formal principles of machine learning. In this module, I'm going to talk more about the empirical aspects of machine practice. So recall the three design decisions for a machine learning algorithm. First, set up the hypothesis class, training objective, and the optimization algorithm. And each of these design decisions has itself a bunch of different. So for the hypothesis class, you have to specify the feature extractor phi, new features, quadratic features, and you also have to specify the architecture. A linear predictor, or to use a one-layer neural network or a two-layer neural network, and how many hidden units do you have when you have a neural network. So for the training objective, there's a question of what should the loss function be, the hinge loss or the logistic loss, and then what about regularization? You use regularization. Should its strength be? For the optimization algorithm, even the vanilla stochastic gradient descent has two hyperparameters. One is the number of epochs. Another one is the step size. Here it's a constant, but maybe you want it to be decreasing, or you want to use a fancier adaptive step size rule, ADAGRAD or ADAM. If you're training deep neural networks, there's more things to think about. There's initialization. How much noise do you add in pre-training? Use a batch size. Stochastic gradient descent has batch size 1. Do you use 4, 16? What about using a dropout rate to guard against overfitting? So quickly, you see that the design space becomes quite big, and it's really kind of like choose your own venture. Some of these design decisions can be made based on principles. For example, if you believe that your data has some sort of periodic structure, you can add periodic features. But many of these, if not most of the design decisions, are really unclear. And you sometimes just want an automatic way for these design decisions made. So each of these design decisions is called a hyperparameter. Hyperparameters are the design decisions that need to be made before running the learning algorithm. So how do you choose these? So how about we choose the design of the hyperparameters to minimize the training error? So this is a really bad idea because the optimum would be to just include all the features, use no regularization, train forever, and really drive the training loss down, down, down. But remember, the training loss is not the quantity that we care about. Okay, so how about we choose the hyperparameters to minimize the test error? So this might generate actually good hyperparameters, but this is also bad because now you're looking at the test set, which makes it an unreliable estimate of the actual error. So what do we do then? So the solution is to use a held out validation set. It's also known as a holdout set or development set. And this set is just taken out of the training set and is used to optimize hyperparameters for analysis. So here's a picture. You leave the test set alone. It's isolated from what you're doing here. And you take the training set and you divide it into a validation set, which is usually a small fraction, but large enough to get reliable estimates, and then the rest of the training set. So now for each setting of the hyperparameters, you can train on this train minus the validation, and then evaluate the validation, and then you can choose the hyperparameters to be the ones that minimize the error on this validation set. So now I'm going to talk about model development strategy. So we've talked a lot about the formal machinery, and I'm just going to walk you through kind of a typical kind of development cycle. So what you do is you start out by splitting the data. You get some data and you split it into train, validation, and test. You lock away the test set, and you look at the data, not the test data, the train or validation data, to get intuition. You want to understand what kind of properties your problem that you're trying to solve has. And then you repeat the following. So you implement a model architecture or a feature extractor, or you adjust some hyperparameters, And then you run the learning algorithm to train a model. And then you look at sanity check the train and validation errors along the way. Make sure the training error is going down, making sure the validation error more or less goes down. If it goes up, that means you're overfitting. You also want to look at least for linear classifiers, the weights, if they're interpretable, get, again, sanity check and get some intuition. And you also want to look at some prediction errors. You want to understand if the model is not doing as well as you like, how is it screwing up? And you repeat this until you're satisfied. And then finally, you unlock the test set, you evaluate on the test set to get your final error rates that you put in your review. So let's walk through an example of how it works. Okay, so I'm going to take this simple example of a named entity recognition. So here the input is a string, which contains a name along with a word to the left and the word to the right to offer some context. And the output is going to be whether X, excluding this initial and final word, is a person or not. In this case, Gavin Newsom is +1 because person. Okay, so now I'm going to code this up. So we have ner.py. So this is a file that we're going to use. And this file actually depends on submission.py and util.py from your sentiment homework. So if you have that, you can plug it in with this code and see it in action for yourself. So let me just walk through this. First, let's read the training examples, the validation examples, and then we're going to learn a predictor. This returns a set of weights. We're going to output the weights to a file, output the error analysis to a file, which I'll show you in a second. And then this part is commented out because we don't want to run evaluation on a test set just yet. Okay, so the first thing we want to do is just open up this training file just to get some intuition for what the data looks like. Okay, so each line here is a training example. This is Y, this is a minus, which means it's not a person. And this is X. Took Mauritius into. Mauritius is not a person. US is not a person. Malaysia is not a person. Sarah Bukowski is a person, +1. Moscow is not a person, and so on. See all these training examples. We have around 7,000 training. Okay, so now let's begin by implementing feature extractor. I have to implement this function. It's going to take X, and just to put a comment, what does X looks like? So example X is the string here. And then I'm going to define the feature vector to be a default dictionary of float. So this is going to be a sparse representation of the feature vector. Okay, so that is the simplest feature extractor. It happens to be the empty vector with no features. Well, let's just see what happens. Start simple. So starting really simple here. Okay, so let's do Python py. We see that across a number of iterations, test error is really high, 72% error. This is not surprising because we don't have any features. Okay, so let's add some features. So maybe a kind of obvious feature to add is looking at the identity of entity. So what we're going to do is I'm going to process X a little bit. So I'm going to split it into a bunch of tokens. So a list containing took, Mauritius, and into. And then I'm going to split it up into the left entity and the right. And this is going to be token 0, tokens 1 through everything except for the last token. And then I'm going to have the last token. Okay, so I'm just going to divide X into these 3 parts. So now I can define a feature template. So let's define a feature template to be phi entity is And then entity is now an array, so I'm going to join it, and I'm going to set that to 1. So this is a binary. This is one line that represents one feature template, but it instantiates into a whole bunch of different features, one for every possible entity. Okay, so I'm naming the feature in a way that makes it really interpretable. So we'll see how this is quite useful in a second. Okay, so let's run this, see what happens. And now the error is 19%. Made some progress. The training error is really low, which means that we're really fitting the training error. So now let's go and inspect what happens. So we look at the weights here. So this is sorted from positive to negative. Here we have the feature name and the weight. So up here, you can see that entity is, and these generally happen to be. And if you look at the bottom, we see things which are not names. Okay, so this is a good sanity check that suggests that the learning is working. Let's look at the error analysis. So this shows you on the validation set the predictions that the model makes. So here is the first input, Gordo Romero. The true label is 1 person, but we predicted -1, which is wrong. And here I'm showing the features that and their particular weights. So entity is a Romero that has a feature value of 1. Its weight is 0. And a weight of 0 generally means that it never saw this feature at training time. So therefore the score is 0, so we have no idea what to do. Example, here is another example of the Senate. It says entity is Senate, and Senate has a weight of -1, so we have a score of -1, and we make a prediction. So let me just look through these incorrect predictions. Margaret Olaf, blamed, was midfielder. And you can kind of see, well, it's unreasonable to expect that the entity being seen before. So why don't we try to use the context to figure out whether the name is an entity, the name is a person or not. So let's go over here. I'm going to define a feature template. Left is left, and right is right. So this is a feature template. Left is blank, as we've written past. And I'm instantiating this feature for this particular x, which is taking the actual value left here. Okay, so I added 2 feature templates. Let's run this. And now we can see that the error rate has gone down to 11%. Great. Notice that the training error doesn't actually go down as fast because with more features, sometimes it's harder to optimize, but that's okay because we don't care about the training error. We only care about the test error going down. One note is that this says test error, but I'm actually passing in here the validation set. So learn predictor, the function prints out test error because it doesn't have any idea where the Okay, so let's look at the weights. So at the top, still features that look at the entity, Clinton, Kelton. Here is some examples. Left is minister. So if you have minister someone, that is probably a person. President someone is a person. If you look down here, you see that if the left context is the weight is minus, which means that the something is not a person. So this all makes sense. It's a good sanity check. Let's look at the error analysis. So now we're getting Romero correct. Let's see what we're getting wrong. So Smith is blamed. Felix Mantilla, we've never, I guess we've seen that person before. Kurdistan Workers' Party, it's never seen this. And now you can think more, brainstorm and think, well, maybe we aren't going to see the exact string match of an entity, but we can maybe break it down pieces. So what I'm going to do is for each word in entity, I'm going to say entity contains word. So it's pretty easy to write feature templates. And this is very intuitive. So this feature template just says, does this entity contain a particular word in the entity? Okay, so let's run this. And now the error rate is going down to 6%. Okay, so we're making good progress. Let's look at the weights. I need to check this. So an entity contains, this feature will fire both for Clinton and also as well as Bill Clinton. And these contains features are generally seem more general and they're given high weight. At the bottom, again, if it has new in it, it's probably like New York or something, and that's probably not going to be a person. Contains newsroom. I don't know too many people who's error analysis. Let's see what's wrong here. We're still getting this wrong. Sometimes you just get unlucky and going on. We're still getting this. Kurdistan party one wrong. Chairman. And sometimes it's kind of hard to know what to do. So let's just try something else. Let's say going in the spirit of decomposing the entity into words, we can go further and have patterns that match on prefixes and suffixes. So we can say the entity contains the prefix word and just arbitrarily choose the first 4 characters. It contains the suffix word, and I'm going to choose last 4 characters. So first 4 characters, last 4 characters. Okay. All right, so let's see how this does. Now we can see that the error rate is going down to 4%. So we made a little bit of progress there. I'm actually going to call it quits for now, just in the interest of time. We've made a lot of progress from 70% error to only 4% error. But remember, this is only on the validation set. So now comes the final trial to see how well this does on the test set. So I'm going to read in the test set and then evaluate the predictor on this test set. And I'm going to print it out. So let's run this and hope that we didn't overfit. And here we actually did even better on the test set than validation set, which sometimes happens. There's just always some randomness here. And so we ended up with 4% error rate, which is pretty good for 10 minutes of work. So in practice, things are probably not going to go as smooth as this. This was just kind of an illustrative example to illustrate the kind of the process here. Okay, so there's much more to be said about the practice of machine learning. So I'm just going to give you kind of some general advice. Many of these tips are kind of related to having best software engineering practices. So the first thing I want to talk about is starting simple. So the wrong thing to do is code up a really complicated learning algorithm, run it on 1 million examples, and watch it kind of crash and burn. Wonder what happened. Simplify, both in terms of running on small subsets of your data, maybe even synthetic data, and also start with a simple baseline model. We started with literally a classifier that had 0 features and maybe 1 feature, just so we can see and understand what it's doing. So this is important because it allows you to work in a regime where things are understandable, and also, importantly, things run quickly. So you want fast iteration time. Like what you just saw was we can quickly try something, get a result, try something, wait a result. If you have to wait 10 hours to get a result, then you're just not going to make as much progress because you won't be ready. One sanity check that I would recommend is try to train on very few examples, like 5 examples, and see if you can overfit. See if you can drive the training error to 0. Now, of course, doing so is not going to give you a useful model, but it will tell you whether the machine learning is working or not. If you're unable to fit 5 examples, that something is wrong. It could mean that your data is too noisy, or you lack certain features, your model is not expressive enough, or your learning algorithm isn't working. Maybe you try to optimize a zero loss or something. I don't know. But anyway, it's a good sanity check. The second thing is log everything. Print out metrics. So track the training loss and the validation loss over time. Make sure that it's going down as intended. Record the hyperparameters that you're using to train so you can keep track of what you actually did to get your result. Print out statistics of the data set, how many features, how many examples, the model, how many weights are there, the norm of the weights, predictions, as you saw. And it was really useful to have this file that showed you exactly how the model made each prediction. It just gives you a lot more insight. Finally, spend some time figuring out how to organize your experiments. I like to have each run I make go into a separate folder, which you can save. And so then later you can go back and check all the models, the predictions, and a record of all of the hyperparameters that you use so that you just have an idea of what you did. And then a note about reporting your results. It's important to run your experiments multiple times, particularly with different random seeds. So you make sure that your results are stable and reliable, and then you can report the mean and the standard deviation over these random seeds. And finally, we often in machine learning tend to be guilty of distilling everything down into one number, test error. But in practice, we might be interested in multiple metrics. In particular, it's important to make sure that if you get 5% error, understand what those errors are. Sometimes it's useful to report the error rates on different minority groups or subpopulations if you have access to that information. And generally be cognizant of the biases in your model. Okay, to summarize, we've talked about the practice of machine learning. First, make sure you have good data hygiene. Separate your test set, leave it alone, and divide your training set into a validation and the rest. Don't look at the test set, but do look at the training or validation set to understand the shape of your data so that you can have intuition for deciding how to model the data. Start simple. And finally, there's a lot of design decisions which can be overwhelming at first. And the most important thing is to practice doing that, doing experimentation so that you can start developing an intuition of which hyperparameters matter and what kind of effect they have. And then eventually developing a set of best practices for yourself. Okay, that's all.